Good evening, everyone, and welcome to another Northshire Presents virtual event. My name is Davith Wood. I am the events manager at Northshire's Manchester, Vermont location, and I'm here as almost always with my good friend and colleague, Rachel Person, from Northshire's Saratoga Springs location. She's going to introduce our author and presenters tonight in just a few moments, but before things go, as you came in, you may have noticed that we are recording tonight's event. But don't worry, only those of us who are speaking and in the little yellow box are going to be on YouTube in perpetuity. So for that matter, for that reason, if you have any questions at any point, type them into the chat, and then Rachel and I will save those up and ask them for you during the Q&A at the end of the session. And finally, before Rachel takes it away with the good stuff, a note of thanks. It's been a hard year, and independent bookselling has not been good for the last many years, or a couple years. So we owe our continued existence to you and your support. So we really appreciate it, and thanks so much. Rachel, take it away.
I am so very pleased to get to be the one to welcome Chad Orzel to our screens this evening. He is a physicist, professor, and blogger, and the author of 3 previous books, all of which are actually very popular titles in my household. They are How to Teach Quantum Physics to Your Dog, How to Teach Relativity to Your Dog, and Eureka, Discovering Your Inner Scientist. He is an associate professor in the Department of Physics and Astronomy at Union College, and he is with us today to talk about his newest book, A Brief History of Timekeeping, which came out just today, so it's a release day event.
Yes.
And he will be interviewed this evening by John Rieffel, an associate professor in Union's Computer Science Department. Please join me in welcoming them both to our screens this evening.
Thank you very much. So I have my screen shared here. I'll talk briefly about the book and the core idea of the book for a few minutes, and just to so everybody's sort of on the same page. I did want to say it's actually very appropriate to be doing this associated with Saratoga Springs, which has a role in an important moment in the history of timekeeping, which is this is a map showing the times in various cities before and after the introduction of time zones, which happened in 1883 in the United States. And the first proposal for a scheme like this one that was initially adopted actually originated in Saratoga Springs with a fellow named Charles Dowd in 1869, and he was the principal of the Temple Grove Ladies Seminary, which is one of the forerunners of Skidmore College. So his particular proposal didn't actually go anywhere, but it is a landmark of sorts in the the adoption of standard time. So it's an appropriate place to be talking about a book about the history of timekeeping. And I wanted to say, though, that when we think about timekeeping, we think about clocks and things of that nature, which seem very technological. But this is actually a history that goes back much farther than you necessarily realize. And the core idea of everything in the history of timekeeping is very simple, that a clock is a thing that ticks, right? It's something that does some regular repeated motion that you can count the repetitions and use that to quantify the passage of time. And the history of timekeeping is really just a history of identifying different things that tick and basing your standards on them at different points. So this starts with the oldest are sun-based systems. So these are a couple of pictures illustrating a sundial and a monument that I'll say more about in a minute. The simplest form of time tracking device you can do is to make a sundial, which just looks at the shadow cast by some vertical object as the sun rises in the east, moves across the sky, and sets in the west. And that causes the shadow to track across the ground, as it's doing in this little video here that I shot in my backyard for an experiment some years ago. And that gives you a visual indicator of where you are in the course of a day. So this is a clock that ticks once a day as the sun moves across the sky, right? But there's also another slower motion to the sun that's very familiar to folks at our latitude, right? Because we're now, it's dark at 4 in the afternoon, because as the year goes along, the sun moves north to south as well. The rising position is north of east in the summer, and it's south of east in the winter months. And that causes the sun to trace out this sort of interesting shape in the sky over the course of a year. If you take a picture of the sun at the same time every day, it traces out this funny hourglass kind of shape called an analemma. And this means that the change in the rising and setting position is something you can also build a clock to mark. And the most ancient kinds of clocks that we have are of this sort. There's these solstice markers. This picture that I had earlier, this is a picture of the New Grange Monument, which is right outside of Dublin. It's a giant artificial hill with a passageway leading to a central chamber. And this is on the right here, you have a picture of that passageway. Very narrow, enormous, massive stones. And once a year on the winter solstice in December, the rising sun passes through a slit over the doorway and casts a ray of light all the way down this passage to this vaulted central chamber in this monument. And that's the only time all year that light reaches the center. So this is a clock that ticks once a year, right? This tells you that you've come around to the winter solstice again. Right. And that tells you one full year has passed. And this is something that clearly people went to enormous effort a long time ago to pile up all these rocks to get a solstice marker that would be a clock that would tell them where they are in the course of the year. So these are the most ancient kinds of clocks we have. This monument was, New Grange was constructed around 3200 BCE. So this is over 5,000 years old, and it still works. If you go there, you can put your name into a lottery to get to be in the central chamber at sunrise on December 21st to see the sun come through and come down the passageway. Though because they're in Ireland, they are very careful to tell you that there are no refunds in case it's cloudy. So. These are the most ancient kinds of clocks that there are. They're based just on the motion of the sun. There are also very ancient technologies for tracking time, like this one. This is a clepsydra, a water clock that was found in Karnak, Egypt. And this dates to about 1300 BCE. And there's actually, this is one where we can actually attach a name to the inventor of this particular technology, which is remarkable given how old it is, because there's a tomb from about 1500 BCE, where a court official named Amenemhet claims in an inscription in his tomb that he invented a marvelous kind of clock that would keep time through the night when the sun isn't visible. And what it is it's this thing that looks sort of like a flower pot with a hole in the bottom, and you fill it with water to some level, and that water drains out, and that the draining of the water provides your tick, right? So and this has markings on the inside you can see reproduced in the right here, with different levels indicating different times. So you can fill this up and watch it drain, right? And that gives you a clock that will tell you, the ticking is and the hours that are marked on the inside. And there's 12 columns of numbers there reflecting the different lengths of the night in the different months of the year. So this is, we're pretty sure, his invention from 1500 BCE. So again, an enormously ancient technology. And surprisingly, these water clocks remained the sort of the state of the art in timekeeping. They were the best timekeepers available all the way up into the 1500s, and really weren't really supplanted until 1657, when people made the first pendulum clocks. And so this is a bit of video of the clock in Union College's Memorial Chapel. That you can see rocking back and forth. This is marking time with the motion of a pendulum, a heavy weight swinging back and forth. And this is what introduces the audio metaphor that I've been using. A clock is a thing that ticks, right? The tick is the gears coming into contact with each other. This really introduces, what we would think of as an ordinary clock. And again, these are still in use, right? I shot this a year and a half ago here at Union. And from there, we moved on to the fanciest and fastest tick of all, which is the ticking of light. Modern time is defined in terms of oscillations of light waves. And 1 second is defined as 9,192,631,770 oscillations of a particular frequency of light that's associated with transition between energy levels and cesium atoms. So this is a drastic shift from the other kinds of ticking, right? It's not one that you can watch with your eye and count by hand, but we have these fantastic technologies developed for measuring these frequencies electronically and converting this to a signal that you can use as a clock. So that's sort of a survey of the history of the technologies that we've used, and that's kind of the core of the book. The book also covers, though, a lot of other things, right? It's fundamentally a history. That means it's necessarily a very human story, which means it's going to involve some politics, right? And like I said at the beginning, right, there are key political processes like the introduction of time zones that was, first proposed by someone in Saratoga Springs. And also various civil and religious calendars in different cultures all around the world. And even gets into some sort of fundamental physics and philosophy, where we look at the way that issues of synchronizing clocks over long distances lead you directly into the theory of relativity, which profoundly reshapes the way that we think about space and time. So it's really an enormously rich history dating back, 5,000-10,000 years that covers an enormous range of stuff. And there's kind of a little something for everyone in here. And so that's sort of my quickie pitch to give you a sense of what the book's about and so on. And I will stop sharing now. And then I think we'll let John take over and ask questions.
All right, thanks, Chad. That was fantastic. Just if you're wondering why a professor in the computer science department is qualified to interview you, you might be delighted to know that for a long time I owned the domain escapement.org.
Oh, really?
Yeah, I lost it in 2014. I stopped renewing it in 2014, so bad timing.
So who got it then?
It's hidden now. But what fascinated me, and so I love reading that chapter in your book especially, well, I guess we'll get to it later, is as a computer scientist, what delights me is that an escapement, from my understanding, is what translates the continuous domain to the discrete domain. It's the thing that ticks, right?
Yep.
So it's hard to know where to begin, but one of the fun insights I had reading your book is how much science was advanced just by trying to figure out how to tell time well. So I wonder if you could elaborate a little bit more on why having so many objects, so many celestial objects out of sync led to so many scientific advancements.
Yeah, that's one of the really interesting things about the development of timekeeping is that it ends up being a hard problem because the cycles that we're using are sort of incommensurate with each other. So, right, we have, a day is a really easy, obvious thing to count. And a year is, a full cycle of the seasons. That seems pretty straightforward. But a tropical year, the time from one summer solstice to the next, is not an integer number of days. So you can't just simply count an even number of days and have a year and then you're done, right? So you have to do something more clever. There's also the cycle of the moon, right? We watch the phases of the moon go from a crescent to a full moon, back to a crescent, and then start over, right? That cycle also extremely obvious if you're outdoors after dark. But again, it's not an integer number of days, and there aren't an integer number of full moons in a year. So people for thousands of years have been working on this problem, how to make these incommensurate cycles mesh with each other, how to come up with some system for, okay, I can count days easily, I can count, full moons easily. How do I get a system where counting days will reliably tell me where I am in the year? Or how do I get a system where counting full moons reliably tells me where I am in the year? And so people have had to play a lot of really interesting tricks around this and develop enormous amounts of math and a huge amounts of effort going into observing carefully, what are the positions of all of the various things we can see in the sky at different dates, and counting, how long before the moon comes back to the same spot, and working out all these cycles to make this work. So, and that's what leads to a wide variety of different kind of calendar systems that are in use even today. So.
Yeah, but like verging on the science fiction or the speculative, do you think a planet where the sun, did fit an integer amount of times into a year, and the moon did fit an integer amount of times into a month, would that have led to fewer scientific advances?
Yeah, I think it would be a lot easier, right? If the Earth went around the sun just a little faster, so it was exactly 360 days, and the moon went around the Earth just a little slower, so it was exactly 30 days, right? Then you would have no problem, right? Then making a calendar would be, super easy, and nobody would have to do this like 30 days hath September, and which are the ones that rhyme with that. So you wouldn't need any of those mnemonics. So yeah, I think there's definitely a sense in which that would make things easier and require less effort, and then perhaps spur a little less innovation in areas of math and astronomy, because you wouldn't need to look so hard to find the patterns.
Yeah. To jump, okay, a few other fun questions. To turn to one of my favorite topics, which is time travel.
I know how much you love time travel stories.
If I had a time machine that used our modern calendar, can you explain what blackout dates I should avoid?
So the issue is, and this is again one of these incommensurate cycle things, right? The first system people come up with that does a good job of just day counting and matching the tropical year is, the Egyptian civil calendar is exactly 365 days, and that comes close, but that drifts by about a day every 4 years. And so over time, the astronomical markers that they used to mark the seasons drifted through the calendar in Egypt. And the fascinating thing is the civilization in Egypt lasted so long that they were able to see like 2 whole cycles of this. It takes about 1,400 years to go all the way through for the rising of the star Sirius that set their new year to come all the way around the calendar again. And they were able to see that happen twice because their civilization lasted so long. The next reform is in the age of the Caesars, right? Julius Caesar introduces the modern idea of leap years, of adding a day every 4th year to February, and that gets you 365 and a quarter days on average for your calendar. And that's actually a hair too long. It's too long by about 11 minutes. And over time, again, over a period of 1,500 years, that builds up. And so that people started to notice that, look, according to the calendar, the equinox is supposed to fall on this day in March. It's actually falling several days later. Something is wrong. We need to fix this. And so in the late 1500s, the Pope calls together a conclave of astronomers and theologians, and they put together a new calendar, which is the calendar we're still using today. It's the Gregorian calendar, which has the every 4-year leap year, except 3 out of the 4 century years get dropped. So 1900 was not a leap year, but 2000 was. So it's a slightly more complicated, but it only rarely ever comes up. But that means that the calendar, right, when they implement this new calendar to get things back in sync, they dropped 10 days. So October 4th was followed by October 15th in 1582. So, if you ever, to get back to your the form of your original question, if you ever have a time machine that uses, you got your DeLorean and you dial in the dates, when you get that, do not dial in, October 8th, 1582, or the car is going to end up, God knows where. Which I don't know, maybe that's the reboot, right? When they inevitably reboot Back to the Future, maybe that's what they do. They try to go visit the Renaissance and they end up picking one of those dates that doesn't exist.
Yeah. All right, we have a question from the audience, which is great. Not that I didn't have a lot of questions prepared, but their questions are more interesting. Anastasia asks if you can explain the Lunar New Year and how do people decide when that starts?
Right, so the Lunar New Year is, a lot of calendars are fundamentally they're lunisolar, right? So they're trying to mesh together the cycles of the moon and the cycles of the seasons. And so the idea is you pick a particular new moon, happens to be in the winter, that you're going to say this is the start of a new year, and then we count 12 months that are full moons, and come back around. The problem is if you do that, you come up something like 10 or 11 days short of a tropical year. So every now and then you need to add an extra month and count 13 full moons for the year. And that means that relative to the Gregorian calendar that we use in the West is based on fixing the locations of the solstices and the equinoxes, right? The shortest day of the year is always December 21st, give or take a day. The longest day of the year is always June 21st, give or take a day, right? If you're using one of these more lunar calendars, though, the start of the year, that the date of the full moon slides around a bit. It slips, 10 days per year. And then every few years, you have to add an extra month, an extra count a 13th moon before you declare it to be the new year. This is actually done on it turns out there's a 19-year cycle. It's called the Matonic Cycle. And this is developed, it's named after a guy in Greece, Maton of Athens, I think. But it's named after a Greek, but like most of the mathematical and scientific things that are named after Greeks, he actually cribbed it from the Babylonians, who knew about it hundreds of thousands of years earlier. And but they knew thousands of years ago that you need to add 7 months in a 19-year span. And so there's a pattern to it. So it's like, 2 12-month years, then a 13th month year, then, 2 12-month years, then a 13-month, then you go 3 years before you add the extra month and so on. This pattern was worked out by the Babylonians. It's used in Greece, and it's the same pattern that's followed by the Chinese lunar calendar. That their Lunar New Year is coming up shortly, and it's the same pattern followed by the Jewish calendar. So they figured out it's 19 years is plus 19 12-month years plus 7 months is matches the full moon cycle.
But Ramadan does something unusual.
Yeah, Ramadan, the Islamic calendar reflects, and this is one of the fascinating things about this, that people in different cultures choose to prioritize different things. So the Jewish calendar and its successors in Christianity are prioritizing matching the seasons, right? And so they're doing this thing where you stick in an extra month every now and then to roughly keep the full moons in sync with the seasons. The Islamic calendar actually just scraps the seasonal part. They say they go strictly on the moon, right? So, a month starts with, if you're being really strict about it, a month starts with the sighting of the first crescent moon. And, that's the date of the month. And that means that the month of Ramadan, when devout Muslims fast, that slips through the year by 10 or 11 days. So story I mentioned in the book, a former student who was actually Shenenda Hoa grad, a former student was an observant Muslim and would fast during Ramadan. And while he was at Union, that was happening in the winter. But he said every year it got a little harder because every year Ramadan shifted toward season when the days were longer. And so the fast was harder. And, every 10 years or so, it comes around into the summer and then it's really unpleasant.
We have another great question from Benjamin asking about the duality of timekeeping and computing and about how the two are often related through mechanisms like the Antikythera mechanism. And he asks, would it suffice to say without timekeeping, modern computers wouldn't exist? And what ramifications does that hold for quantum computing?
So I think that there's definitely a connection there because right, the Antikythera mechanism is an ancient mechanical computer, and what it's doing is it's using gearing to match these incommensurate cycles. So you have gears with different numbers of teeth that sort of interlock with each other. And as one completes a cycle, it turns another one, which takes a different amount of time and goes through a different number of cycles. And you can match these things up and do something fairly sophisticated where you can track out, you can use it to predict eclipses, which it turns out also happen on about it's close to a 19-year cycle. It's 18 years and some months that eclipses repeat over. And so, this is, again, a thing that you can do. And there's a lot of ingenuity that goes into doing that mechanically. I don't think that that's not a very direct ancestor of modern computers. And that you look at somebody like Babbage's calculating engines, those are doing the same sort of thing with gearing, but they didn't know about the Antikythera mechanism at the time they did that. They were coming up with that on their own. But it definitely builds out of doing clockwork calculations. These things, anything where you're doing cycles, right? It kind of makes sense to start doing these gears, and fundamentally, like you're repeating these calculations over and over and over again, right? To project things out into the future. That gives you a strong incentive to automate the process, right? There's a nice bit in. I mentioned in the book, it's from one of Kepler's books about doing the calculations of the orbit of Mars. He says he goes through the calculation and then he says, apologetically to the reader, like, if you feel like this was horribly boring, I agree, but take pity on me. I had to do it 75 times. So, you're repeating these calculations over and over. That gives you a real incentive to find a better way to do it. And that drives toward computing. And so I think there really is a connection there.
So because that was 3 questions in one, I think we'll skip ahead a little bit to a non-controversial question asked by David. On the balance, actually goes to your opening slide. Is daylight savings time beneficial to society?
So I get asked this a bunch when I'm doing promo for this. And what I've been saying is one of the many things that will keep me from ever holding elective office is my position on daylight saving time, which is I like the fall back option. Like getting an extra hour of sleep in November is great. We should do that. We should keep that part. But the spring forward thing is what messes it up. And also I like, right, having the sun rise before 8:30 in December is good. Like I like that. And having long evenings in the summer for, baseball games and picnics and all that, that's really good. So if we can keep those, that would be great. But it's that spring forward that's the problem. So my proposed scheme is we keep the fall back. We drop back an hour on one Saturday in November. But rather than springing forward an hour in March, starting at the winter solstice, every Saturday after that for 12 weeks, we move the clocks forward 5 minutes. And the logic is, 5 minutes a week, you lose 5 minutes of sleep a week, nobody's even going to notice that. Right. So it's not that big a deal. And over 12 weeks, that gets you back by March, that gets you back to the place where we've moved the clocks forward an hour. And now we get the long days in the summer. And so you sort of keep the fall transition because that gets us some extra sleep. You spread out the spring transition, and that gets us the benefits that come from this time change system. So more painlessly. So this is, of course, way too complicated for anybody to vote for, and that's why I'll never get elected to anything.
All right. I was also delighted by, well, let's see how to introduce this. So every now and then I've been known to accidentally arrive at meetings, an hour late or an hour early. But I was delighted about how arriving someplace a day early led to an invention of a very effective water clock.
Yeah. This is a narrowly averted diplomatic incident in medieval China, and so there's one of the most impressive clocks, maybe the single clock that I'm most impressed with in the book is this tower clock that's built by a guy named Su Song in China around 1100. And he did this because he was sent on a diplomatic mission to a neighboring kingdom to offer greetings on the winter solstice. And he arrived a day early because the calendar system that they were using in China was a day off at the time. And so it was nearly a disaster because these barbarians that he was going to visit had a better determination of the solstice than he did. And he managed to talk his way out of it. But when he came back to court, he first of all had got the timekeepers all sacked and presumably punished. And then he set about making sure that was never going to happen again. And so he built this enormous tower clock it's based on a wheel that was 10 meters across that was powered by water. So they had a constant flow water source. And then it's driving a giant wheel with buckets at the end of the spokes. And it will sort of position one of these buckets underneath the water. As it fills up, when it fills up to a certain point, it would tip and trip a locking mechanism that would release and allow the wheel to rotate, pulled down by the weight of the water in the buckets. Would rotate one spot, bring an empty bucket into position. The locking mechanism drops back down. The new bucket fills until it tips, and then it turns the wheel one more spoke, and so on. And so it's this monumental clock that this tower 10 meters high that is built in Kaifeng. And it powered a celestial globe showing the positions of the stars that was synced to rotate with the actual sky, and an armillary sphere so they could more easily do observations, and also had public facing displays. So there were figures holding cards that said what time it was, and drums and bells and all that kind of stuff, announcing the time to people in the city. So it's really an amazing achievement, and sort of a nice demonstration of how even, this is over 1,000 years ago, or it's around 1,000 years ago. People were placing enough importance on accurate timekeeping that, arriving one day too soon for the solstice greeting was going to be a diplomatic crisis that justified this enormous effort afterwards.
Has anyone ever been able to replicate that? I know it was destroyed and they tried to rebuild it.
The actual original clock didn't last very long. It was only about 20 or 30 years before that dynasty fell and the city was captured by somebody else. And then the new people couldn't make the clock work. But he wrote an extremely detailed book about how the thing was constructed and how it operated, which, you know, still survives. And so you can, if you look on YouTube for, you know, Su Song Tower Clock, people have made modern replicas, followed his instructions and built replica clocks. And so there's some great YouTube videos of, you know, somebody in China has made a, you know, a 3/4 scale replica of the thing, and it works great. It really works very well. So.
That gives me a good segue into one of my next questions about synchronizing clocks, right? It's important nowadays that we all agree what time it is everywhere. As I learned the hard way when I realized that the deadline for a conference paper I had was due in Australia time. And
yeah,
I had
that's a good one.
20 minutes instead of 12 hours in order to finish it. It wasn't funny at the time, but can you explain a little bit the process by which people in distant locations can agree what time it is and why it's harder than you might think?
Yeah, so the tricky thing is, right, and it's the graphic I showed at the beginning, this map of time zones in 1883. It's a little hard to read, but in the small print, it shows a bunch of major cities, each of which has its own local time. So the time in New York City is like 5 minutes different than the time in Washington, D.C., which is 5 minutes different than the time in Charleston, South Carolina, right? And so there's time is a very local thing based on where the sun is in the sky at a particular location. And that's great as long as nobody can travel very fast. But, you know, by the 1860s, right, in the US, you could easily get on a train in New York City in the morning and, you know, by sunset, you're in Ohio where the sun is setting a full half hour later. And so then it becomes an issue where you have to think about synchronizing these clocks over significant distances. And you have to be able to do that in a practical way because people can start to experience it. Right? It's a problem even earlier because it matters for navigation. Right? If you want to find your longitude, you need to know the difference in time between where you are and where somebody else is. But, you know, when people are really caring about the longitude problem in the 1700s, the rise of European empires, right? It's weeks to go from one to another. So it's not an immediate problem. The procedure that you develop once you've got fast communications and fast travel involves sending signals back and forth. So if you want to synchronize two clocks in two different positions, you have one of them send out a signal saying, okay, it's noon. And when that signal arrives at the other clock, they set their clock to noon, and then they send a signal back saying, got it, it's noon. And then the people at the first spot, when they receive that, they look at how long it took those signals to make the round trip. And they say, okay, the difference in time between us is half that round trip time, or, you know, the travel time is half that round trip time. And then they send another message back saying, okay, correct your time by half that round trip time. And then you end up with the clocks in sync. Right. So if it takes 10 minutes for a message to go from one to another, right, this one sends a signal at noon, this one receives it at 10 after 12, sets their clock to noon, so they're 10 minutes slow. When the signal gets back, it's now 12:20, and they say, okay, bump your clock ahead 10 minutes, and you're good. Right. And so that's the procedure by which you can get clocks synchronized. And this works really great, but you have to account for that travel time. And that becomes really important. That leads into the theory of relativity, because this changes as you start to deal with people who are moving around.
So it gets more complicated if one person is standing still and the other one is on a spaceship?
Right. So what happens is that procedure works great to synchronize clocks for two people, and it's not that one of them starts moving, right? Because they would notice that, right? That, you can't synchronize the clock with a person on a train that's getting steadily farther away, because this is going to be a mess. But if you have a third party who's moving relative to the first two, watching them synchronize their clocks, they're going to see something very different. They're going to see that, while the signal is in flight from one to the other, one person is moving toward it and the other's moving away from it, right? In one direction, rather. In one direction, the recipient is moving toward the signal. It's going to take less time to get to them. In the other direction, when they send the signal back, the other person is running away from the signal. It's going to take more time to get to them. And that means that the round trip time, according to the person who's moving, looking at this, is going to be different than the round trip time according to the two people who are doing the clock synchronization, which means that the person who's moving relative to them is going to look at them and say, you've done this wrong. Your clocks are not, in fact, synchronized. And that problem gets worse the faster the moving observer is moving, and that problem gets worse the farther apart the clocks are. So you find that it's impossible to synchronize clocks in such a way that everybody, both stationary and moving, agrees that the clocks are synchronized. And that's the essence of relativity. It turns out you can get, right, the Einstein's theory of special relativity, right, famously weird theory where it tells us that moving clocks tick slower than stationary clocks. It tells us that moving objects shrink along the direction of motion, right? You can get all of the weird effects of that just from having a set of clocks that are out of sync with each other in the way that you get from this synchronization process gone wrong. So that's a path into the theory of relativity. It was actually really before Einstein. It was spelled out by Henri Poincaré, was the first one to really make this connection between that synchronization process and the timing, the missynchronization that arises when you start considering these moving observers.
So to delve back into science fiction, does this have implications for my planned intergalactic empire? Like, will we be able to synchronize clocks in as humanity spreads across the galaxy?
Unfortunately, no, because one of the keys to this is that it relies on the speed of light being a constant, and the speed of light travels. Light travels at 299,792,458 meters per second. And that's the same everywhere in every direction, no matter how you're moving, you'll see light moving at that speed. So sending the signals from one end of your galactic empire to the other is going to take you, hundreds of thousands of years to synchronize the clocks. It's just never going to work very well. And then the people on the ships who are moving between different star systems, hopefully at speeds close to the speed of light, if they want to get there anytime, while they're still breathing, they're going to see everything get all messed up. So your interstellar empire is going to be a mess.
So the first thing you do when you get some places, you set your clock.
Yeah, probably. If you could do that, right? If you could travel between different star systems, probably, then you're back in the era of local time. Just wherever you arrive, you say, okay, what year is it? What time is it? Okay, go. Now we synchronize our clocks when we get in the same place, and then we're okay. There are some fascinating fictional approaches to this. There's people who, there's a lot of science fiction that's sort of crap on this front, right? Where they just have magical drives, so you just disappear in one place and end up in the other place, or it's functionally like taking the subway. But there are people who've actually thought seriously about this and like what kind of things you would do. This. And I can't remember the name of the book, but Alastair Reynolds has a cool book with, there's a group of people who just like orbit the galaxy. They at high speed, and they drop in on different systems every few thousand years to see what's going on. And there's another Werner Vinge has a good universe where people are moving around, and they've put some thought into what do you do about the fact that you know, it takes different amounts of time on the ships that are going from one place to another than it does in the systems they travel between. So you have like the Cheng Ho in those books. So.
All right. We have time for more questions. The chat's been a little quiet. So if you've been worried about running out of time to ask your questions about time, we have more time.
Yes.
Otherwise, I'm going to have to resort to asking Chad for help programming the clock on my VCR.
Unfortunately, I'm not going to be much use for that. What I would say is, you know, like get a, you know, if you get a modern phone, right, it's got the time right there. So you just use that and forget about the VCR.
A Saratoga specific question, if I can jump in with that.
Absolutely.
Which is the gentleman you were speaking about earlier who came up with the idea of time zones. Is there a little marker to him behind the Adirondack Trust branch on Broadway? Do you know if that's him?
I don't know. It's like a Charles F. Dowd. So he was in charge of the school in the 1860s. Okay. And so he's significant enough that if you Google him, he pops right up on Wikipedia. And so it would not at all surprise me if there was a marker to him. I think he was a meaningful figure in the history of the seminary, which then evolved into Skidmore. So.
Okay, and actually Patricia says in the chat that yes, that is his marker behind Adirondack Trust. It's a globe sundial. It's very cool.
Yeah. Yeah, he ended up he couldn't get the attention of anybody in in power to you know, anybody with the power to do it. He pitched the idea to the railroads of doing time zones, and the railroads in 1869 said, nah, it seems like a hassle, we're not going to do that. What changed it is actually in the 1870s, there was a guy named Cleveland Abbey who was at the forerunner of the National Weather Service. And he had this network of people doing weather observations, and he kept having trouble synchronizing their efforts because they were recording him in this patchwork of local times. So he said, you know, we really ought to do something to standardize the time, and approached a group called the National Meteorological Society for it. And they said, great, you're chair of the committee to standardize time, which they thought would get rid of him. But he was a federal bureaucrat, so he knew what he was doing. He put together a committee, he recruited a bunch of other people. And one of the people he recruited was somebody with the railroads, who was in charge of coordinating timetables for the railroads as a whole, who said, you know what, we should get on this, because if we wait until one of these people convinces Congress to do something, Congress is going to mess it up, and they're going to come up with a system that's going to be inconvenient for us. Let's just make our own time zone system. And so they developed this system of time zones that's based on railway line boundaries. And so there were rail networks that only operated in the eastern US and others that only operated in the Midwest. And where they butted up against each other, that's where they drew the line. And so the railroads negotiated this, they imposed this on the rail networks, and then they talked cities and towns and states into joining on to their system. So the time zone system that comes in the 1880s it's implemented in the most American way imaginable, which is, you know, large, powerful corporations decide to do a thing on their own so as to preempt politicians doing anything about it. So.
It seems like there's a real communications aspect to that in terms of like getting people to actually, like, it's one thing for the railroad to say we're doing this and to get a city to say, but then to get people to actually jump on and understand it and do it. Was that a challenge that they faced?
There was some blowback for a while. They had trouble, like Maine and Ohio kept dropping in and out of the system for a little while because they're at the extremes of the Eastern time zone, and so that's where the differences are largest, and people complained about it. But you know, like people are fundamentally kind of lazy, right? So you know, you're gonna have a clock or a watch, right? You're gonna set it by whatever is the most convenient source, and so you know, so there are big public clocks in railway stations. There's big public clocks in towns, right? You're going to set your clock by looking at one of those. And, you know, once they're all synchronized with the railroad clocks, then, you know, everybody else just kind of goes along. Yeah, there was some complaining about it for a little while, but everybody just sort of goes along. That happens even with the more dramatic shifts, like, you know, the mentioned earlier, the episode where they put in the Gregorian calendar and they dropped 10 days from the calendar, right? That went remarkably smoothly. And even a couple hundred years later, when they put it in the UK, by that time they'd had another year where that was a leap year in the Julian system and not in the Gregorian system. So when the British put the calendar system in, they had to drop 11 days from the calendar in 1750 something. And that's so there's a famous painting that sort of, there's some claims that there was mass chaos and riots, and there's a famous painting where somebody has a placard that says, "Give us back our 11 days." But it actually, as far as anybody can tell, there isn't really like mass civil disorder at this time. Like, it mostly went pretty smoothly. Like there were some landlords that tried to charge 30 days rent for a month with 19 days in it, and there's, you know, some other people who tried to weasel out of paying debts that they owed, but you know, that got sorted out in the courts, and otherwise everybody was just kind of like, okay, well, so we're saying it's the 16th. Okay, it's the 16th. Like, you know, and it just go
along. That's probably a great place to end, right? So, so before I forget, available at your local independent bookstore, Brief History of Timekeeping. It's a fantastic book. I highly recommend it. And Chad, thanks for taking the time to talk to us.
Yes, thank you for being such a generous interviewer.
Chad, John, thank you so much. This is a fantastic event. We really appreciate it. You can order the book, A Brief History of Timekeeping, at northshire.com. Have a great evening, everyone. Thank you all so much.
Thank you.
See you next time.
Thank you. Good night.